welcome to this video. This is 5-2, and in this video we are going to talk about increasing and decreasing intervals of a function using calculus. We're going to go ahead and start off looking at a graph here, f of x, and it says consider the function above. On what intervals is f of x increasing? On what intervals is f of x decreasing? Now, you can easily recognize that a function is increasing when it is moving up from left to right. So here we can say that f of x is increasing on the interval 2 to 5. And I'll go ahead and include those endpoints, and we'll talk about including those values here in a moment, as well as union 7 all the way to infinity. So that's where my function is increasing, where it is moving up from this interval 2 to 5, as well as 7 to infinity. All right, now where is the function decreasing? Well, a function's decreasing when it is moving down from left to right. So looking at this function, I know the graph is decreasing from -3 to 2, and I'll include those values. Again, union from 5 to 7. Okay, and so those are where our graph is increasing and where it is decreasing, where it's moving down. Now, there is some controversy about increasing and decreasing intervals, but let's go ahead and look at this idea. There is often confusion about why we include endpoints when discussing increasing and decreasing intervals. The confusion really is due to a misunderstanding of what we mean when discussing intervals of increasing or decreasing behavior. It's important that we understand we are not ever claiming or discussing a single point. We are not ever claiming a single point on the graph is increasing or decreasing. How could one point be increasing or decreasing anyway if we just look at specifically one finite point? Rather, we define increasing as a function f is increasing on an interval whenever the next point is greater than the point before it. Okay, so for f of b is greater than f of a for all b greater than a. More simply, we must include all x values where the current point is higher than the point right before it. Okay? This means that even at points where the graph seems to stop increasing, we must include those x values in our interval since that point is still higher than the point right before it. We can define decreasing intervals in similar way. So although this is talking about increasing intervals, decreasing intervals is in a similar manner, which is why we used closed intervals for a function, both increasing and decreasing intervals, except for the infinities, right? For the infinities, we would leave those as parentheses. We're not going to include them. So when we include the endpoints intervals, don't be confused and think that we are complaining that the function is increasing at that point. We are only stating that the point is still higher than the point right before it or after it, okay? So that's just kind of a disclaimer here. Why do I include the endpoints here on my increasing and decreasing intervals? Okay, so looking at the graph of f of x, it's really easy to see where it's increasing and decreasing. However, in calculus, we generally do not have a graph of f to look at. What properties of f could help us determine where f is increasing and decreasing? I'm going to go ahead and show you the graph. I want you to pause me. What properties can we look at to help us go ahead and determine where a graph is increasing and where it is decreasing? Okay, hopefully you paused the video. What I hope maybe that you observe is that a function is decreasing when it's going down, or where f prime of x is negative. That's going to be decreasing. Now, I know a function is increasing when it's going up. It has a positive slope. So f prime of x is greater than 0. That's an increasing interval. Okay, now what separates these? Like, when do I change from increasing to decreasing? And hopefully you notice that we have these points here, here, and here. So the main idea is that we have, when f prime of x is equal to 0, we're going to call these critical numbers, and we'll cover this here in a moment. Okay, critical numbers. Now that occurs down here at this value. I have a derivative of 0, as well as these values. Here my derivative is not 0, my derivative's undefined, or f prime is undefined. Okay, so these are the points where a graph can change from increasing to decreasing. It doesn't mean it always changes, but sometimes it does. Okay, so hopefully you picked up on that. Let's go ahead and focus for the start of this video on the critical values. A critical value, if f of x is defined at x equals c, has to be defined, then f of x has a critical point at x equals c if f prime of c is equal to 0, or if f prime of c is undefined. Okay, so we're going to go ahead and here in example number 1, we're going to look at the critical values for this function h of x. Okay, so the first thing that we want to go ahead and do for h of x, I need to investigate. To find critical values, I have to look at the derivative. So I need to find h prime of x. So I'm going to go ahead and use my quotient rule. The derivative at the top is 1 times the denominator minus derivative at the bottom, again, which is 1 times the numerator, all over x plus 2 quantity squared, okay? And if I go ahead and simplify this, the x's cancel, and we just have 2 over x plus 2 quantity squared, okay? All right, so I want to know two things. Where is this function equal to 0? Where is h prime of x equal to 0? So what I can do is I can take my function 2 over x plus 2 quantity squared, set that equal to 0. I can go ahead and solve by multiplying both sides by x plus 2 quantity squared. This cancels, and we end up getting 2 is equal to 0. Well, 2 is never equal to 0. So this never happens. Never. So I don't have a slope of 0 ever for this function. Okay? And another way too we find zeros, especially with rational functions, if you remember, we just set the numerator equal to 0, because when we're canceling out the denominator, when we multiply by the right side, nothing's going to happen on that side. So just remember that shortcut. We have 2 is equal to 0. Now, I'm going to go ahead and I'm going to look at undefined. Where is h prime of x? Undefined. Now remember, this is when our denominator is equal to 0. If our denominator is equal to 0, it's undefined. So I can go ahead and I can set my denominator, x plus 2 squared, equal to 0. Now this just gives me two factors set equal to 0. So really, I only need to investigate this once, but we have two zeros at the same location, or sorry, two critical values at the same location, -2, and this is a critical point, okay? However, remember that a critical value must be defined. A critical value must be defined. So I'm going to say here, x equals c must be defined. So this one is really kind of a nuance. Notice that in my function x cannot equal -2 because it is a vertical asymptote. This value is excluded from the domain. So in this case, we're going to say h of x has no critical points. Has no critical points. Well, that was a pointless example. You get it? No? Okay. Example number 2. Here they say let f prime of x equal x minus 1 cubed times e to the power of 2x. Find any values of x where f of x has a critical point. Okay, so my critical point again comes from f prime of x being set equal to 0. Where is f prime of x equal to 0? So I'm going to set each piece of my function equal to 0 using the zero product property. Okay, so I have that, or I have e to the power of 2x equal to 0. And again, this is x minus 1 cubed. Really, I only have to investigate x minus 1. There's just 3 of them. And if I go ahead and solve, if I add 1 to both sides, we get x is equal to 1. Okay, so f prime of x is equal to 0 at 1. And e to the power of 2x equals 0. Well, this never happens. Never. Okay? So we only have one critical value. We only have one critical value. Okay, so we can go ahead and say f of x has one critical point value number at x equals 1. As far as undefined, like where is my function undefined? This function's defined everywhere because we have x minus 1 cubed. That's a polynomial, so that's defined everywhere. It's never undefined. So I don't have to look at that case, okay? So there is our critical points. Okay, what was the point of finding the critical points? Well, I need the critical points to help me find where to investigate for increasing and decreasing intervals because they break these up. Now remember, if my derivative, if f prime of x is greater than 0, that's a positive slope. The function is increasing. If my f prime of x is less than or equal to 0, we say that that function is decreasing on that interval, okay? So, how do we go ahead and find increasing and decreasing intervals? Well, here are some steps. Step 1, you're going to find f prime of x. Step 2, when is f prime of x equal to 0 and when is f prime of x undefined? You need to investigate those. Number 3, you're going to go ahead and create and label a sign chart for f prime, and then you're going to go ahead and test the intervals. Number 4, you're going to go ahead and interpret the sign chart and to find the appropriate intervals, okay? So, helpful tip. If given a graph of f prime of x, you do not need to create a sign chart because the graph is a sign chart. However, a sign chart can help you read or interpret a graph. So we'll come up to the graphical examples here in a moment. Here's example number 3. They say let g of x equal x squared minus 3x minus 21. Find the intervals where g is increasing and decreasing. Okay, so step number 1, I need to go ahead, I need to find f prime of x. Sorry, not f, I should say g prime of x. I'm going to take a derivative. 2x minus 3. Next, step number 2, where is g prime of x equal to 0? So I can go ahead and set 2x minus 3 equal to 0, and I can solve this. 2x is equal to 3, x is equal to 3/2, which is 1.5. Now, what about undefined? Well, g prime is defined everywhere. It's never undefined. It's a polynomial, so its domain is negative infinity to positive infinity, so I don't have any values. Step number 3, I'm going to go ahead and I'm going to make a g prime number line. I'm going to label it. There's g prime. My critical value, 1.5 or 3/2. Okay, now I need to go ahead and I need to test. The best numbers to test are 0 and 1. And sometimes it helps to get away from a critical value because you can see relationships. Remember, all we're doing is we want to see positive or negative. So I like 0. I'm going to go ahead and test 0. What is g prime of 0? So that's 2 times 0 minus 3 That's -3, negative. So I know my function's decreasing there. Okay, and then what other value do you want to test? You could test 2. You could test for anything on this interval. Let's test 10. Let's get a bigger value. So g prime of 10. So I have 2 times 10 minus 3. And I don't even have to compute it. Is this relationship, is this quantity bigger than 0 or less than 0? Well, 2 times 10 is definitely bigger than -3. So this is greater than 0, and this is positive. What does that mean? Okay, well, we can go ahead and say, here's number 4, here's our conclusion. G is increasing on -infinity to 1.5. If you like inequality notation, you could say this is the same thing as, is it t or x values? X values. X is less than or equal to 1.5. And then we can say, ooh, what am I doing? That's decreasing. Decreasing. And then G is increasing on 1.5 to infinity. And again, you could say this as x is greater than or equal to 1.5. Okay? So there you have it. That's increasing and decreasing intervals. Example number 4. Same question. They say let h prime of x equal x minus 2 times x plus 1 quantity squared. Find the intervals where h is increasing and decreasing. Okay, well again, I just need to go ahead. Step 1, I need to find h prime of x. And that's already done. X minus 2, x plus 1 quantity squared. So now I'm going to set that equal to 0. X minus 2 equals 0 times x plus 1 squared. Again, this implies that x minus 2 is equal to 0. So there's one critical value. It also implies that x plus 1 is equal to 0. So x is equal to -1. Okay, so there I have my 2 critical values. Now, is h prime of x ever undefined? Investigate this. Are there any discontinuities that I have to worry about? No. So my critical values, right, that was step number 2. My critical points are -1 and 2. Okay, so let's go ahead and let's test. So obviously here I'm going to test 0, I'll test -10, and I'll test a +10. So I say, okay, what is h of -10? If I go ahead and plug this in, -10 minus 2 times -10 plus 1 quantity squared. Now here's a trick. I'm just going to go ahead and say, okay, is the relationship positive or negative? Well, -10 minus 2, isn't that negative? -10 plus 1, that's negative, but I'm squaring it. -1 squared, so that's going to be positive. A negative times a positive gives me a negative. So I know that this interval is negative. We can go ahead and test 10. So h prime of 0. Oh, I forgot my h prime here. This is h prime sign chart. H prime of 0. So I go ahead and plug this in. We get 0 minus 2. That's negative. And then we have 0 plus 1 squared. Hey, that's positive. So this is negative. This is negative. So still negative on this interval. Okay. And then lastly, I'll go ahead and I will test h of 10. Let's see if we get a positive one here. So 10 minus 2, okay, that's positive. And then we have 10 plus 1 squared, that's positive, so this is positive. Positive. Okay, what does that mean? What does that mean? Well, it means that h is decreasing on -infinity to 2. All of this is decreasing. So I'm going to use all values, negative infinity to 2, and h is increasing on 2 to infinity for all of these values. Okay? All right. Number 5. They say, let k of x equal 2 sine of x minus x. Find the intervals where k is increasing and decreasing, where 0 is less than or equal to x, less than 2 pi. So I'm using trig here, and in trig, remember it's cyclical, and it occurs in waves. It's periodic. So what they often do is they restrict your domain 0 to 2 pi, which is nice because that's the unit circle. So I'm going to go ahead, step number 1, I'm going to find k prime of x. K prime of x equals 2 cosine of x minus 1. Now I want to set this equal to 0. So when is 2 cosine of x minus 1 equal to 0? I'll move my 1 over, so I get 2 cosine of x is equal to 1. I'll go ahead and divide by 2, and we get cosine of x is equal to 1/2. Okay, so now I need to go ahead and I need to use my memory. Where does x equal 1/2? Where does my x value equal to 1/2? Well, if I use my left-hand trick, here's my left-hand trick. If I go ahead and make my x value 1, here's my x value is 1, then that's occurring at this angle, which is pi thirds. So at pi thirds, cosine of x is equal to 1/2, as well as in quadrant 4, right? Where your x values are positive, and that's going to be at 5 pi over 3. Almost 2 pi, right? 1 pi third back, okay? So here's your critical values. Here's critical values, k prime. And I'm going to say pi thirds. This is 5 pi thirds. Here's 0, and here's 2 pi. So I'm going to go ahead and I have to test on these intervals. So at 0, let's test before pi thirds, pi fourths. Pi fourths is always nice. Maybe at the quadrantal, a pi half. And then here, ooh, 5 pi thirds. What are we going to test there? Well, this is periodic, so I know it's going to kind of oscillate as a wave. So let me go ahead. I'm going to test pi fourths. So what is k prime of pi over 4? And that was 2 cosine x, which is pi over 4 minus 1. So here we have 2 times root 2 over 2. Those cancel. Root 2 minus 1. This is positive. It's a positive relationship. Okay. K prime of pi over 2. Okay. This is going to be 2 cosine of pi 2, which we know is 0. 0 minus 1. That's negative. And this value is going to be positive. You could plug back in 2 pi if you're thinking about critical values oscillating. 2 pi is to the right. So if I plug in 2 pi, we have k prime of 2 pi, which again is 1. So 2 minus 1, which gives us a positive. Okay, so I have tested there. Okay, and then that tells me my increasing, decreasing intervals. So I can say k is decreasing on pi thirds to 5 pi thirds, increasing on 0 to pi thirds union 5 pi thirds to 2 pi. Okay. All right, we are almost done with this first part on increasing and decreasing intervals. I want to briefly go ahead and talk about graphs. How do you interpret this on a graph? And be careful on the AP exam. Here's an AP exam tip. It's the graph usually given is f prime. They usually give you a derivative graph. And always just make sure what you're looking at. So here this graph is f prime of x. So whenever I'm interpreting for f, is f increasing? Is it decreasing? Well, I'm not interpreting the slope of this. I'm not going to do what I did up here where I took a derivative and I set that equal to 0 to find my critical numbers. I'm already given the derivative. This is like some of those ones where we were already given the derivative. So again, I'm going to go ahead and they want me to do the same thing here. They say consider the graph of f prime above where f prime is the derivative of f. Find the intervals where f is increasing and decreasing. Okay, so using that same system, f prime, where is f prime equal to 0 or is it undefined? Well, it's equal to 0 at -4. And it's also equal to 0 at -1. And it's also equal to 0 at 1. I don't have any undefined, no non-differentiable points here. And then where is it positive? Where is f prime positive on this interval? -∞ to -4 in this interval. Well, isn't it above the x-axis? So that's positive. Here, from -4 to -1. Well, isn't it above the x-axis? So f prime is positive. Between -1 and 1, it's negative. And between 1 and positive infinity, it is positive. So, what does that mean? Well, we can say f is increasing on -∞ to -1 union 1 to infinity, and decreasing on -1 to 1. There you have it. Super easy. F prime, super, super easy. Example 7. Consider the graph of g prime of x above. Where is g prime, which is the derivative of g? Find the intervals where g is increasing and decreasing. Okay. Go ahead. I want you guys to pause the video. I want you to try this one on your own. All right, hopefully you went ahead and you tried this example. Now, I want to talk about the critical values first, looking at this graph. G prime is equal to 0 at these x values, at 1, 3, and 10. It's also undefined at 2, 5, 7, 8, and 12. Holy smokes, that's a lot. Now, this is what the tip was saying early on in this video. If you're given a graph, I don't necessarily have to make a G prime sign chart, a number line. I know G prime is positive when it's above the x-axis, right? So I'm looking, where is G prime, when is it above the x-axis? Well, up until 1, it's positive. After 3, it's positive. Not after. That's the interval. That's where it's positive. Okay, where is it negative? When it's below. From 1 to 3 and from 10 on. Okay, so there's your statement. We can say G is increasing on, let's say x is less than or equal to 1. And 3 is less than or equal to x, which is less than or equal to 10. Just kind of switching it up to inequality notation on you. And decreasing on, not -1, 1 to 3, and x is greater than or equal to 10. There you go. All right, that's going to be it for part 1. In this video, we talked about the ideas of critical values. How do I use a function in symbolic form to find the critical values? And then, how do I use those critical values to ultimately tell me where is my function increasing and where is it decreasing? Remember, a function's increasing if f prime of x is greater than 0, slope's positive, and it's decreasing where f prime of x is less than 0, where the slope is negative. Give me a thumbs up, like the video, subscribe. Catch part 2 of increasing, decreasing intervals.